Okay, hello to the second day of the HPC workshop. Today I will talk about the basic parallel algorithms in the theory part, and for the hands-on part, we will do something a bit different. We will just continue with running jobs on the cluster. I'll show you how to run parallel jobs, like as in how to run multiple programs in parallel, how to run a single program with, let's say, different parameters. If you're doing parallel scans, but still using a serial program. And for tomorrow, we will have the basics of OpenMP and basics of MPI programming. So it will be, I guess, more hands-on, more of programming. Yeah, okay. So, fundamental parallel algorithms. What do I mean by that? So if you know classical, or let's say sequential programming, you know that, or it's possible to kind of divide your programming commands into control patterns and computing patterns. So computing patterns, that's really manipulating the numbers, solving some equations, or like assigning a number, doing some arithmetics on it. And control patterns, I would say, is basically everything else, maybe except input and output. So control pattern is something that defines the flow of your program. And classically in sequential programming, the easiest control pattern is sequence. That's really just one command after another. So an ordered list of tasks or command which are carried out in that order. And again, we're talking sequential stuff. So one task is executed at the same time. And that's really, in most programming languages, that really just means you write those commands like on separate lines, and like the computer executes them as it reads them. Then you have a selection pattern. That's basically branching. So you have some sort of condition, and depending on that condition, you have a selection of commands to be executed, two or more. Traditionally, that's an if statement. And finally, iteration, that is, you have a certain function or a piece of code, a certain sequence that is to be repeatedly executed as long as some condition is valid. So that's while and for statements, loops, basically. And out of these three, you can already make a lot, basically most of almost all of the programs, if you also include inputs and outputs and the arithmetic operations. In parallel world, wait. So what I wanted to say also, I had a slide for that. Out of these, if you want to parallelize your program, what do you think would be best parallelized? Like what kind of control pattern is parallelizable, and what kind of control pattern is not, at least not easily parallelizable? What do you think?
Selection.
Selection is what? Yes or no?
It's better for parallelizing.
Selection.
Yes. Okay. I think it would be quite better. Iteration is
yeah. So selection is not very well parallelizable. Because you have this data flow issue. So if you have a single piece of data and you come to an if statement, then you're deciding, I mean, if you have several pieces of data and an if statement, and that if statement depends on the data. So for some pieces, it might be true. For some pieces, it might not be true. Then you have this branching issue where for certain kinds of parallelization, like vectorization, for example, you need to execute a different part of code for each of the piece of data. And so in some cases that might work, but specifically in this vectorization case, you really cannot do it at all. I mean, there are tricks in some specific cases, but in general, the easiest one is iteration, where like conceptually you are doing the same same sequence of operations on that data. Sequence is for a sequence it really depends, because sometimes the sequence is parallelizable if the subsequent commands do not depend on the results of the previous commands. That might be true or it might not be true. Really depends on the exact algorithm. So like, and you will see that for iteration, it's also not that simple, of course, because if it were simple, we probably wouldn't be having workshops on that. So in parallel world, the most common piece of code you were trying to, or in data parallel applications, you're trying to parallelize serial iteration, and serial iteration has a lot of those fundamental offsprings, let's say, equivalents of iteration in the parallel world. I will talk about the really most basic ones, that's map, partition, reduce, and scan. And then very common patterns are decomposition patterns. These since we are parallelizing iteration, those patterns are, let's say, on the level of algorithm or let's say instructions, while the decomposition patterns are also live in the world of data. So they are not applicable to serial code. Why? Because I'll talk about pipeline, briefly mention superscalar sequences and domain decomposition. So let's take domain decomposition just quickly. Domain decomposition means I have a domain that's my full all my data. That's what I call a domain, and I split it into smaller parts and distribute that among individual workers, and suppose that those workers can work in parallel. Now, if I can do that in serial code, I can decompose my domain, and then what happens? Like, I still process it serially in parts, but even those parts are being processed serially, so I basically didn't do anything. If I split 1,000 points into 100 buckets, 10 points each, and then do 100 buckets in parallel, that's nice, that's cool, that's parallelization. If I still have only serial code, I will do first bucket, second bucket, etc., up to the 100 bucket, and it's the same as if I just had one big bucket and went over all those all the elements in this whole large bucket. So let's continue with those parallel patterns. The easiest one, the easiest idea is a partition. So partition can be thought as some basic way of domain decomposition, but very specifically, it's a case where I treat multiple items, multiple data points together. So I have a large array and I split it into small partitions so that, for example, each of the partition will fit into my vector register. And I do it specifically if I'm talking about partition. Those subcollections are non-overlapping. So it's like exclusively partitioned. In case of overlapping collections, we'll talk about this later, that would be the proper domain decomposition. So that's like a very general idea, but it's behind a lot of other algorithms. So the second fundamental algorithm is so-called map, and map is very easily just applying the same function to multiple elements at the same time. So, for example, if I want to multiply an array of values by a constant, by that mean I want to multiply each of the elements in that array by a constant, I can use this map function. So my function is, I can map that multiply function to that array. So when I talk about function here, I mean multiply by 2, let's say, and I map that function, I map that multiplication on the array. If it's just like I said, so there are no interdependencies on other data, then I can obtain a linear speedup with the number of computational elements. That is number of elements which can be processed in parallel. If they cannot be processed in parallel, that means, for example, if I were not multiplying but by 2, but by some value that depends on the value of the previous element after multiplying. In case it can be done, it's obviously something that can be that will scale linearly. With those loop dependencies, that's something that can prevent me from having a linear speedup in the map, or which can prevent me, which can completely prevent me of mapping that function in parallel to my array. So loop dependencies are situations where the result of your loop iteration depends on some the result of some previous iteration. Those come in those dependencies only appear when you're also writing to your array. So if you are not changing your input array, then this will not appear. But if you are, then you have these 3 basic types of dependencies. So first is read after write. So I am writing to the variable at index I, and then reading that variable from the previous iteration. So in my iteration 1, I saved something in A1, and I'm using A0. Okay, it's probably hopefully fine. But in my iteration 2, I want to write in A2, and I need to use A1 for that. But if I were to do it in parallel, I don't know what is in A1 actually. Is it that the new value has this already been processed or not? So it can be the new value, it can be the old value, it can be if this is not just about and it can be a completely incorrect value because for some very distant index, this should have been some large number because this should have been like accumulated over 100 numbers, but only 50 were performed when I actually came to my index 100, for example, or something like that. So this problem cannot be done in parallel at all. I mean, yeah, if it's like this, then you're out of luck. This is your serial piece of code, and it will limit the parallel efficiency of your program. So there's another one right after write. In the same loop, I write to different pieces of the array. But it's right after write, so I'm not writing before my array, just like in those which are forward in that array. Can this be parallelized?
Well, if on different iterations of this for loop we do not use the same elements of an array I, but here we do, like there's a sub I and a sub I plus 2. So on the second iteration from this, we'll be using the same element, like writing inside of it.
Yeah.
But not actually using it. So
no, yeah, but writing is using. I mean,
I mean, not using the variable inside of it, like the value, but interacting with it.
Yeah, but if I want to write somewhere,
it's important that no one else is trying to write there at the same time.
yes, and that's something that cannot be done. It's let's say in the case of vectorization, if I have if I first make a partition where I put my pieces of the array in a single vector, and then I would do this, then I would be constantly rewriting I mean, again, this is not a good example for vectorization either, because at some point I'm over my vector index. But let's say we solve this somehow. I'm still accessing I'm accessing a piece of the vector after I'm accessing that piece of vector at 2 times. That would be what I was doing in serial code. In the vectorized code, I'm doing it at once. So again, I will be missing the effect of one of the I will be basically rewriting that effect conceptually, rewriting it because it happens at the same time, but because I'm rewriting it, I wouldn't see the effect of the first call. This is a bad example because here the first call actually has no effect. For that, you would also need to read at least the I variable here, or this should have been AI, not just I. But it is possible to do it with threading. You have to be cautious, and I will show how to do that tomorrow. And finally, this one, right after read. So I'm using the values of the elements which are like which have a higher index in the array to set the value of my actual element. Can this be parallelized? it's like kind of like an opposite situation than here, where I was using the previous element to set my current element. Here I'm using the subsequent elements to set my current element.
It's still the same problem. Like, we're trying to.
This is a bit tricky because this in general, you can see that, of course, if now it really depends on the order of operations, right? Yeah. But it only gives us a problem if we don't know what is what's being executed before and what's being executed after. Because if I go in a serial way, then I'm never depending on something that has been changed previously. I'm only depending on stuff that's not been changed yet.
In this example.
Hmm?
In this example,
In this one.
we cannot see the mouse.
Oh, sorry, the last one.
Yes.
The last one, yeah.
Mhm.
So I'm only depending on stuff that has not been changed yet. And that means that if I would know that element 10 will definitely not be processed before element 9, then I'm fine. And this would be the case of vectorization, for example. Because with a vector, if I read the whole vector, I can fix its value, use it as an input, and then write to that vector at the same time with this result. And the result is correct. Because my inputs were correct, the inputs didn't depend on the previous iteration. So
Then we will need to make like a copy of this, like of this array A.
no, well, yes, but that's what happens in that instruction. So in the instruction reads reads the data into a register, performs the operation, and uses this as an input again, stores it in some register, and then copies it into the output register if it's written like this. So if in this specific case of vectorization, I know that it cannot happen that I would change element 10 before I'm reading element 10. But it's not the case in let's say threading, for example, because if the thread can execute at any time, so it can first try to modify, it would first modify my element number 10. And when thread which is responsible for element number 9 comes there, it's wrong again. Yeah.
But still, we will need to allocate a memory to store this copy of A, to simultaneously take it out, and then perform something.
Okay. Yeah.
Iteration one by one will have just like 2 places of memory for each values, and we are moving them. Like we need space to only one element of array A, and then if we do it simultaneously, we need to allocate the whole space for the whole array, to take it as one whole piece, and then do something with it.
Yes. So this, if you did it like this in memory, in computer memory, made a copy and operated on a copy, used the copy as input, then your output would be correct, even in the threading case. That's a way how to overcome this in the case of threading. In the case of vectorization, you don't really need to do it because the input register for this kind of operation is not the same as the output register. So it's basically the CPU does this for you. It reads that vector into a register, performs the operation, stores that result somewhere, and then puts it into back into the register. So this will work for vectorized code, basically just as it is written here. But I probably mentioned it last time. If you write your code to be vectorizable, then you can very easily convert that vectorized code into threaded code. Very easily means that, and you will see that tomorrow, that you can just put some, it's called a pragma instruction in C or in C++. You just put this pragma in front of your for loop and tell the compiler, for example, that there are no aliasing dependencies like this, and then it can automatically vectorize your loop. You can do the same with a different pragma to make that loop automatically threaded. So if you have vectorized code, you might be tempted to just like rewrite all the vector pragmas into thread pragmas and hope that it will work. But you can encounter situations like this. Well, it will not work. So again, this was for the idea of map, which is easiest equivalent of a for loop or a while loop. But even with this easiest equivalent, we're already encountering some gotchas coming from the fact that we're doing more stuff at the same time. Second basic basic parallel algorithm or fundamental parallel algorithm is called reduce. And a reduction is a combination of elements into a single result using some predefined combining function. So for example, sum of all elements, very typical one. Or finding a maximum of an element in a collection. Again, this can be done just you have a function that tells you the maximum which element is greater, the one I stored somewhere or the one I'm looking at, and I always store the bigger one into this like temporary storage, and at the end I have a I really have the maximal element of the whole array. So this combining function is typically a binary function uses two operands. In that sense, map is applying a single operand function on the whole array. And this can be parallelized, of course, but in a little bit of a clever way. And you won't get a linear speedup anymore because you need to do those comparisons, but you can do those comparisons first in like always between two elements in pairs like this, and then do the comparison in pairs on the results of those original comparisons. And so with this, you arrive at the at your final result in log n steps if you have n processors. But you can also see that it's not an optimal algorithm in the sense of utilization of your parallel machine, because a lot of processors have nothing to do near the end. So, but it's a very typical one, and a very typical situation is when you combine those two ideas into a single algorithm map, so-called map reduce algorithms, and it's so common that in many programming languages you have libraries that are specifically designed to do map reduce operations on different architectures, be it GPUs, multi-core CPUs, clusters, grids, and like almost every architecture, every parallel architecture definitely needs this, and most of the programming languages have. There are of course ways to optimize this in case it's not just a simple algorithm, but you have also some branching in there, and that is some selection which cannot be like easily parallelized, but those libraries operate on this in this basic MapReduce idea and give you some tools how to make it how to implement it in more complex situations. So with MapReduce, I first apply a function to all those single elements, and then pass the result to this combining reduction function. So typical examples: how many times does a word appear in a text? So I split the text into chunks in words, and distribute those chunks again among my processing units. And so that's partition. Partition is part of it, but it's not usually mentioned in the name of this algorithm. It's kind of implied. Then I map a counting function on those chunks. So the function counts the words, and for each chunk gives me number, how many times that word appeared. And then I call the reduction function, which just adds the counts from each of the processing units. Another example, finding a norm on some large n-dimensional vector, where I have p workers, and my n is larger than p, so each of the workers gets n over p numbers, and each of those workers uses the map function will find the squares of each of the vector components and add those numbers which they have been assigned to, and the reduce function can will add those sub results, because the squares are always like just like simply edit all of them. So it's a reduction again on addition. And in the end, I again need a serial operation, this time on this single number, but I have to do the square root. So for this to actually be a norm, you can see that this map function is here partially performing the same thing as the reduce function. Theoretically, of course, I can just have the map to make the square roots, but then I would need to have n workers for an n-dimensional vector, and do the reduction on the squares instead of having this doing already part of the reduction algorithm. And again, with this simple ideas, you can already implement a lot of typical serial algorithms with this combination. So now, what about that loop where the result of my ith element depended on the result of my previous element? Can we really not find some way to parallelize it? Yes, actually, we can, but you cannot parallelize it just by saying just by saying do the inside of this loop in parallel, like randomly on some of the elements. You really have to plan how to approach it, and of course it depends also on the commutability of your function on the of the operation that you want to parallelize. This algorithm is called either scan or prefix sum. Okay, kind of forgot what's if it's the same. Scan is the same as prefix sum because yeah. Yeah. So I mean I'm really now just doing this this loop so that each element depends only on the value of the previous elements, and the scanning function or this prefix function is commutative. Then what I can do is in a structure like this, I can add again first operate in pairs, and basically you're propagating the number to each of your elements, but only from like from the start to the end. So if you watch how the zero, no, okay, this is zero. So, but how this element would propagate. So in the first step, I get it to the next element. That's fine. Then because it has been added to this element already, it will get here to the fourth element in the second step, and together with this first element number 1, I'm counting from 0 again, so to element number 3, and to get it to element number 2, I do this step over, like interleaving in one element. So I got it. This is a short array, so here I already got into the half of that array. But then if I do a step over interleaving 4 elements. So here I was interleaving on 0, here on 1, 2. I'm leaving out 2, and here I'm leaving out 4. Then from here I get it here. Here it got from the third one. Here. Here is where did when do I get it to this one? So here is obvious that comes from okay, I don't see the path from here to here. Maybe the image is wrong, or do you see that?
0 to 2, then 2 to 9.
Then
And 9 goes up to
Yeah,
12.
but there is no connection from the 0 to 12.
oh, here to 12. I got it in
From the
this step. That's
second
fine, but
zero,
to this, which is 13 at this point. I don't know if I'm missing the step in the picture. Come on. Sorry. Of course it gets D because it's already counted here. This is it's 0, so this is still 2, but this 0 has been added to this element already in this step. So this is how it gets here. Yeah, I do the addition from the beginning till the end. So I need to propagate this number. So yeah, here I get so here it got from here to here. I add it directly here. This element is reading it from the modified value of this element. This element is getting it directly here. This element gets it from the modified value of this one. This gets it from the modified value of this one, which has been modified here. And the last one got it through this path. Yeah. So again, this is in log n steps, but you cannot do it just by saying execute this function at once. Right. For scan and same as with MapReduce, also for scan you will find a lot of libraries that implement this. For OpenMP and MPI as well, there are special functions that perform scans, that perform reductions. Mapping is kind of like a natural thing because you just write the body of the loop, and that's already a map. If you just say, okay, do this for all elements, and yeah, for reduce and for scan, you will find some OpenMP or MPI primitives because those depend on the also on communication patterns in both cases. So these are the basic patterns that allow you to just like read your sequential code and rewrite it in parallel again if there are no data dependencies and issues that will make it not parallelizable. Then but the other way, if you find code which is using those scan and MapReduce algorithms, then it's very easy to rewrite it into serial code because like all of these have some counterpart in the serial world as well. There are some other patterns, those which I said have no equivalent in the serial world. Again, if you just run that parallel program on one processor, then you're basically getting a serial program, but there's like no concept of those additional ones which I've talked about. So those will be the superscalar sequences, domain decomposition, and what was the third one? Yeah, okay, it will be on some slide. So let's start with superscalar sequence. What's a superscalar sequence? It's basically a fancy name for a task graph. So you have some work which where the data flow isn't like just a linear data flow. So that my function reads some data, produces the data, and the next function uses exactly that data to go forward. But you split you draw your program as a graph with data flow dependencies. So here the arrows just show you that you take the output of something, either reading from some variable or a result of a function, and use it as an input for some other function. And After you define those data dependencies, this draws a graph like this. This is a case of serial execution. So like in time, we go from top to bottom, and you use some library which has a task scheduler, and you give those tasks to that library, and the library decides which of those tasks can be done at the same time, because their inputs don't depend on the outputs of some previous task. So, well, like here, for example, these two only depend on what was coming from this f function, so they can be done in parallel. Same as for these two. This S cannot be done in parallel with anything else. I mean, like those can take a long time, so like in parallel with P and Q, but it definitely has to be done after H and R. So you kind of compress this graph in time and distribute those different tasks among your individual computing nodes. So this is a typical case of task parallelism, not data parallelism. Then there are domain decomposition methods. Right? Okay. So another typical method of decomposing your data domain, basically, is called divide and conquer. So divide means I have some problem, like for example, searching through a list, or making yeah, okay, no, you realize. So I have some big problem which I can divide into smaller sub problems which are independent. So I divide it into a set of independent sub problems and solve those sub problems concurrently. And the conquer part is as soon as I find that, I mean, I'm in divide, I'm still doing the division, dividing the problem into smaller problems. And as soon as I find a problem that is small enough for my computing node to solve on its own, I solve it. And then when all the nodes provide their solution for the smallest problems, I start merging this those results into and somehow finding the solution to the big problem from the sub results of those smaller from the results of the smaller sub problems. That's a very general concept, and we've seen one manifestation of that concept already in. Yeah, this is basically a MapReduce algorithm is one instance of a divide and conquer concept. Any MapReduce algorithm, basically, because for the divide there is implicit, because divide is basically partition, and conquer is then basically map. Not necessarily. It can be something different. Like this conquer part doesn't need to be the same function applied to each of their elements. And merging then is this reduction. Another divide and conquer strategy is domain decomposition. I again, it's like third time I think I will talk about it in a few slides, but keep that in mind when I come to it. Okay, this is a very kind of specific specific way of operating on data. Has any one of you solved differential equations on a computer?
Like numerically?
Yeah, numerically. Yeah.
Yeah.
Yeah. So you might remember something like a stencil, or maybe not. Like if you're solving differential equations, some types of differential equations, you have some input array, and like this numerical differentiation basically means that you're replacing this infinitesimal small dt with some delta t, which is like, let's look at the next cell, or let's look at five next cells if it's a higher order differentiation. And this is some differentiation. I mean, sorry, solving a differential equation, that is integration. So solving a differential equation in 2D, and this would represent some sort of central difference in 2 dimensions. So what I need to know is I'm modifying or I'm solving for the middle, the blue cell, and I need to read from those cells, just those green cells around me, and this shape defines what's called a stencil. So a stencil would be a shape that tells me if I'm looking at a certain position and need to find a solution for this position, which first the shape of the stencil, that is which of those neighboring cells I need to take into account. So in this case, it's this one, this one, this one, this one, and maybe probably also the one like at the same index. And with that, it also contains the coefficients of like how much is each of those cells contributing to the solution of this one. If you define this stencil object, so this shape and the coefficients, then you can map the stencil on your array, and then you're back at the map idea, and you can also divide your whole box. That's the further domain decomposition in some subsequent slide, and do this independently. I mean, independently in case that the blue element I'm writing to is not actually in the same array as those green elements. So I have some source term, and I'm the result of the integration is stored in some different array than the one from which I read the inputs. This is a very, very common task. I mean, in physics, solving differential equations is again something you will find. I think I'm not exaggerating if I say like thousands of libraries in almost every programming language for like solution of differential equations in general or in some specialized way. Of course, if you were to program this on your own, because you have like your own special set of differential equations, part of some specific algorithm, so you don't want to use a library for that, because again, like this is, I didn't say it explicitly, but there's this one thing every programmer should know. If someone has made it before, it's usually better to use that thing that has been made before than trying to reinvent the wheel.
Yeah.
But it's not always true, because sometimes the wheels you find around just don't fit. And sometimes the wheel is such a small piece of what you need that like importing the whole wheel factory just because of that is not a good idea, and it's better to write that thing by yourself. And those differential equation solvers, because some of them can be extremely difficult and incredibly complicated, and it can be software with like millions lines of code. Sometimes it's a simple thing for like 10 lines of code. And if that makes sense in your own algorithm, then it might be better to write it by yourself. It's usually an easy thing in serial code, probably like something you would see in one lesson in, I don't know, some numerical methods, master lessons, or maybe even bachelor lessons. They're really not difficult. To do it in parallel, of course, adds some level of difficulty. And here, yes, you are accessing the neighboring items. So if all your data doesn't live on the same processor, you need to know what to do when you're at the end. So for example, if this line is somewhere else than this line, as the solution here requires some communication to the other processing unit. And of course, you can treat this as some additional local boundary condition.
I just thought of another example of such idea where this can be used, like the convolution operation in convolutional neural networks. When you have the kernel,
Absolutely.
and you need to move it through the grid is your picture in pixels.
Yeah. Thank you. Yes.
If it is not parallelized already in TensorFlow or PyTorch.
Yeah, convolution can be also thought as a stencil operation, basically. And with the same elements as I said, right? Because for convolution, I have this like shape of like what I'm convolving, and like for each pixel, I will have some function that modifies that that neighboring pixel, right?
3 by 3, and you are moving it with some step towards all of the picture. You can move it because you are storing the result of the convolution somewhere else. You can move it like simultaneously over many ways.
Yeah. Thank you. Good point. Okay, so finally, domain decomposition. I talked about it a lot, and I talked about it a lot because in physics, this is again something extremely common. And not just in physics, image processing is also a very good example of something where you can apply domain decomposition. And again, the general idea is basically trivial. I divide a data set into subsets which are computed independently. Sounds easy enough. Of course, there's a lot that can go wrong. There's a lot to think about when you would actually go to implement something like this. So first, subsets which are computed independently. So what if some independencies actually exist? If they do, you try to rethink the algorithm in independent steps, which are separated by some communication step that resolve the dependencies. Now, this might not always be possible. If it's not possible, then you cannot use domain decomposition. It is basically easy like that. But in many cases, it is possible. And then you have to think about how to implement those communication steps. So if I go back to the stencil, cancel. So yeah, let's say here's my division line. I decided that I will put this data on one processor and this on another and solve those parts independently. Can it be done? Well, not really independently, because in order to see to set the new value here, I need to see the old value at the neighboring processor. So I need to ask the processor, hey, what's your value here? I need to have this synchronized somehow. So if I'm using message on the message passing level, on node level, I literally ask the neighboring node what's the value in the cell here, and it should like send me that value as a message. So for like MPI message passing or domain decomposition, my original domain is distributed among 4 nodes in this example. And if I need to know the value of the cell on a neighboring node, I need to send and receive a message. If I am doing threads, threaded shared memory communication, I will be writing and reading to those pieces of shared memory. So if I need from here, if I'm storing a value here and I need to know the value here, I can just look in there. Yeah. The good thing about shared memory, again, I'm forgetting a lot of stuff I will talk about. I don't know if maybe at the end or maybe tomorrow. And that is again some data races, data dependencies, as I shown previously, because I need to, of course, make sure that the value I'm sending and receiving and still here the value I'm reading has been already written if it should have been written, and has not been written if it should not have been written at the time of while I'm reading that. But like pairing this, thread parallelization has this nice property that it can be thread domain decomposition with shared memory has this nice property that it can be either done in a static or dynamic way. Static means that basically same as here, where each node received some predefined piece of the array and only works on that predefined piece. I can also give those threads some static predefined limits and let them only operate within those limits. Or I can do dynamic decomposition where those limits change between those iterations, or like I say, even during a single iteration, because I can, instead of using 3 threads, I can use 6 threads. If I divide it here, I can use again do another division, 12 threads, each only with 2 cells, for example. And while that might be useful if I have okay, cannot make up a really useful example on this simple one, but let's say your threads operate on 2 cells at once. Or no. Okay. Let's say your threads operate on 2 cells, and the reason they do it is because your vector processor has some vector instruction which is super optimized for vectors of size 2 of your specific data type here. Then you spawn those 12 threads, and they can continuously. But also you only have 4 cores, so you only have 4 threads, each for 2 cells, and they just being dynamically assigned to those cells as they progress. When one worker is free, it will get assigned to the next free one, etc. So you can use the division into 12 subdomains and operate with 4 threads on those 12 subdomains. And you don't need to know if for example, this and this and this is always operated on by thread number 1, because you can assign that thread anywhere because you have the shared memory, and that's something you couldn't really do with message passing, or you could, but there would be a lot of communication if you were changing those boundaries and exchanging those values so that the nodes have those new boundaries as you want them assigned. So basically, for the message passing variant, I mean, communication is a very expensive operation, so you want to avoid it. So if your domain size changes, it can still be useful, but you have to be sure that the benefit of changing the subdomain size outweighs the cost that you incur by the need of sending those additional cells between the nodes. Yes, large multidimensional arrays, specifically in the context of differential equation solvers, but in many others, also with the convolutions, that would be the same thing. If you want to distribute them using node, like on the level of nodes, then this is a very common thing how to implement this communication operation. So if I know, for example, that I always need to know the I'm setting my element here with the knowledge of the element before it. That's in this direction, so I need to read this in order to set this. I can use so-called halo cells, where I store the value from my neighbor in that halo cell. So I basically do this duplication of this shared part, and when my algorithm runs, I first again, this is the idea. This is not like a data dependency in the same matrix, because that would need some different treatment again. But it's this dependency of the type I read here at this index from this array, but I store at this index in a different array. And for that, in order to do it here in the red region, here in the red region, I need to know the values here from the blue region. And what I do is I store one more line in the red node, and between each steps, I send a message from the blue node to the red node, and that message contains only this this line that has to be shared. This can of course be also two-way. It can be more than one line, for example. So in the end, I have a domain decomposition with overlapping regions. And while I'm here calling this algorithm embarrassingly parallel, it's not really an embarrassingly parallel algorithm. Is one which has like no need for communication. But let's use this definition a little loosely and say it's with little or no need for communication. And that's basically this. This concept. Yeah. And again, you will encounter this very often in differential equation systems, in I don't know if really like image manipulation, probably if it's like a really, really huge image, because you need to put it on a distributed memory system. This doesn't, I mean, this can be useful in shared memory systems as well, but usually it's a typical distributed memory pattern.
Maybe some kind of satellite image that has very high resolution.
Mm,
So it's
yeah.
really a huge one.
Yeah. Okay. Now I will just briefly talk about some specific methods which you might encounter, again depending on what field of study you're doing. Yeah, I'm basing it a lot about on stuff that's useful for differential equations, because I've been doing differential equations for most of my life. So very, very common method, multigrid. So again, I'm solving a differential equation on some grid, and my method is, for example, an iterative method where yeah, in order to get the correct result, I need to do many iterations, and some of these iterative methods, like their convergence, and the speed of their convergence might depend on the quality of my initial guess. And in some of those cases, you can make a good initial guess if you first solve the same or a similar problem on a coarser grid. And if you like go to a coarser grid, you just come to something like you can start from a single number, and then from that do those like finer grids, and use those results of those of each of the refinement as this initial guess for your next refinement. Yeah, now I was talking from my head and not reading my own slide. So yes, first I use this coarse grid, and yes, with the coarse grid, hopefully the solution will quickly converge, because it's a small problem. Here I mean converge quickly as in it doesn't take much time to solve it. Then I increase the resolution of that grid and use when I increase the resolution, then I need to find the values for the new points. Like I use the old points as the initial values, but since I have more points and some of them have no value assigned, I need to find it. I will just interpolate between those close parts of the grid, and I continue refining the grid until I finally reach the maximum resolution I needed at the beginning. And yeah, hope that this initial guess helps me converge faster or converge at all. Those yeah, two comments that, of course, those methods can again get like extremely sophisticated, and again you'll find a lot of huge software packages for doing multi-grid methods. Yeah, you can imagine that sometimes you restart, you find your, I don't know, not converging as fast as you thought, so you restart with this coarser grid again and switch between working on the coarse grid and on the fine grid. Yeah, and the coarse grid also helps you to get the information from distant parts of the domain faster to the place where you're actually solving the solution. Typically, in differential equations, this is for boundary problems, where something like a Poisson equation, for example. So in a boundary problem, you have some value set at the boundary, and you have some sources of something. So let's say it's the Poisson equation. So you have your charges in your domain, and you need to find the electric field. But if it's like a static problem, then the electric field at any of those points is affected by the charges, which can be on the completely different side of that domain. So in order to solve this, you somehow need, at each point, you need to know some information from all the other points in that domain. And like on the first guess, this looks like something that like cannot be efficiently parallelized, right? Because at each point, I need the information from all other points to like solve it correctly. And this is typically where the multigrid methods are used, and where this fact that with the coarser grid, I can quickly get at least some information, not precise, but at least some information from a very distant domain very quickly to my domain, and then work with that, and then refine it in subsequent iterations. For example, specifically for those Poisson solvers, this is not just something that makes the Poisson solver work faster on like large systems. It's something that even like makes it possible on a large system, because otherwise you would be struck with this fundamental issue of needing to know everything to correctly solve for your local point. So kind of like conceptually, this is way to overcome this problem. That is kind of like how it looks. Then you have a processor that's solving a 4x4 grid on the finest variant, and in those coarser grids, it will have a 2x2 system and a single point system and use this single point system as an input, and those single points will then be solved by some other, because again, like this would mean that I would need to communicate in order to solve each of those points. So that might be a very communication-heavy algorithm. But another way is to put all the blue points on a single processor, solve for the blue grid on a single processor, and then distribute the blue points and let the individual processors to continue on those finer subgrids on their own. So that's a very, very typical numerical algorithm that you will encounter. And the final one is not a numerical algorithm, but let's say a control algorithm. Something I said before, that if you do domain decomposition on a distributed memory system, then it's very expensive to change the way that domain is decomposed, because you need to send the cells over the network. But sometimes it might be beneficial. It might be beneficial in case your domains, for example, don't contain just pieces of a Cartesian grid, but combine a Cartesian grid with okay, with particles, for example, which can freely move through the grid. Those are so-called particle mesh methods. And in those particle mesh methods, you can easily divide the mesh among your processors, but those particles can live anywhere inside that mesh. So some processors will have a lot of particles to process. Some processors may have no particles to process. And if that happens to you, then it might happen that your cluster is underutilized. So you have 10 nodes doing all the work and 100 nodes doing nothing. So not only this wastes electricity and cluster time, and your colleagues will be angry when they find out that you're occupying cluster with doing nothing. But of course, it also slows down the operation, because if you have some better distribution, then this would have been computed faster. The problem is that if your particles move and they can move among the nodes, you can have this optimal distribution at the end of the simulation. But in 1,000 steps, you're in like some extremely suboptimal regime. And in that case, you can do redistribution of those particles or of those elements among the nodes. So again, many ways to do that. In a distributed memory system, again, you can find some library to do it for you, or you have to program it yourself, because the way to do load distribution on load balancing on a distributed memory system is exactly as I now said. You need to pack your stuff, your particles, and move them from one node to another, and you need to think about how long it takes to do that operation, and if it's really beneficial to do it, for example, at every time step, or if you just do it every 100 time steps or something like that, because this communication operation can be pricey. In case of a shared memory system, load balancing can be automatically by some scheduler if you partition the problem into a lot more parts than the number of available threads. As I've shown previously, you have 24 boxes and just a 4-thread processor. Okay, that's a very old example. So you have 1,000 compartments and 128 core processor. So you run 128 threads, and some of them will arrive at a compartment that's more difficult to solve than the other compartment. So it will spend a lot of time there. But meanwhile, the others, while waiting for that thread to solve a compartment which takes 10 times more, they will solve 10 of the smaller compartments. That's and again, that's something. I mean, maybe you got already this feeling that that threading is kind of fundamentally easier than message passing, because there's a lot of, because you have the access to the shared memory, everyone can see that shared memory. There's no need to think about how to pass that memory around. Of course, there are more issues with data races than in distributed memory context, but another good thing is that the operating system scheduler and the basic library can already do a lot of this like housekeeping stuff for you. But again, it's only usable if you can actually really physically. I mean, it's only a good option when you can actually physically access the whole memory from your CPU. When your problem is much bigger, then you need to scale to multiple nodes, and then you have no other option than to use distributed memory algorithm. And in that case, it's still, again, nothing I'm saying is like all-time 100%. But most of the time, it's still beneficial to have shared memory parallelization on each single node, even if you're doing distributed, if your problem is so big that you using distributed memory parallelization, as in because this distributed memory MPI, you can run a distributed memory MPI program on a single computer. Then it's like running, I don't know, 16 programs at the same time. They exchange the messages. They exchange them fast because it doesn't have to go through the network, but they can like just put it in memory somewhere, and the other process takes it from there. And a lot of software is actually parallelized that way. So it's a distributed message passing system where each of the workers is a serial program that exchanges messages with other workers. And you can run those workers on the same machine or like on distant nodes. Most often, it's more effective, more efficient if on the single node, you're actually doing a proper shared memory parallelization. So you have a single process on a 16-core computer. You have a single process that has 16 threads, and that 16-threaded process communicates with other 16-threaded processes on different computers, instead of having 16 processes on each computer, which all somehow communicate with one another. But it also means that then you're thinking about those two levels of parallelization, two styles of parallelization at the same time, which of course makes it more difficult than writing a single a serial program with message passing, and then you go into a threaded parallel program with message passing. So obviously, the second thing is can be much more difficult. It's somehow more difficult every time. Okay, so that would be all for today. Any questions? Comments?
Just a lot to take in.
Yeah, it was a lot of stuff, I know. Yes, I mean, like probably each of those slides could be expanded to like a full 1-hour lecture.
Yeah.
But I wanted to I wanted more to give you like an overview of all the topics that are around, because I mean, some of those, like at the beginning, we had those like super fundamental things like MapReduce and scan. Like very likely you will actually never implement your own MapReduce and scan. It's like those sorting algorithms, bubble sort. Heard about it. So it's like this, like you're looking for a job, yeah. You go for a job interview, and the interviewer asks you, oh, do you know bubble sort? Yeah, I know. Like it's like, okay, can you like write down the implementation? And like it's nonsense, because like you will never need to implement bubble sort in your life, in the very specific case that you will really need it because you're in some super weird computer architecture and like sorting I don't know what custom objects. Then you'll just Google it and like look at Google, oh, this was this thing. So to ask this way is of course a stupid question, but at the same time, someone say, hey, this uses bubble sort. Can we use quicksort instead? Can we or not? Maybe you can, maybe not, because quicksort is not stable. And does those things that you need to know that something like this exists and has some properties. So yeah. And it's the same with all the advanced topics. So like load balancing, multi-grid, whatever. You'll find it somewhere, you'll see it, and you should know, at least somehow know what it's about. So not about doing one semester of lectures on multi-grid methods, because not even one semester might be enough. It's like can be multiple PhD theses actually.
It applies to many things, like you just need to know that this stuff exists and to have some basic like background to understand it to some extent. And then when you need it, you'll find it.
Yeah, that's what I hope you will take from
Yeah.
from this workshop. The second part will be again like more hands-on, like really like practical stuff on the cluster. Yeah. So no questions? No comments?
I think that I will renew the presentation and maybe it will come.
Yeah, of course. I will share the presentation to the Telegram group as well.
And
You can go
there
through
will
it
be
again.
the recording as well on YouTube.
Yeah.
I'll publish the first day today and maybe the second day also today.
Okay.
Fine.
Okay. So for the online people, welcome back. And yesterday I know some of you had problems because you were not on Windows but on a Mac. So there was some issues with connecting to the cluster. Have you solved this? Is everyone of the online people also able to connect to the cluster? Maybe, hopefully. Okay, in that case, I will not. Yeah, in that case, I will not flex with my Linux setup and continue on this school computer. And at some point, I would like to show you how to use SSH keys so that you can connect to the cluster without entering the password. And it's something extremely handy when you're working on a terminal. So if you're on Linux or macOS and you're using terminal commands to like copy stuff around, then it's of course handy if you don't need to enter the password every time you do that, and instead use SSH keys for the authentication. The issue is I don't know how to do it on Windows, so I would say let's leave that for the last day when we can do it, because on the last day it will be more individual work instead of like me showing something and then everyone basically just watching, but we will do it in some more interactive way. But
And I think you are not sharing the screen.
I'm not sharing the screen.
Because
Because I've
because
changed
of
the Okay. Yeah. So let's continue with the hands-on session on the cluster. For that, I need to first find which window had notes for today's session. And yes, and when another thing, I have like small HTML website kind of with notes for the hands-on session as well. But it's one I based on operating our cluster in Germany, which has a lot of like differences in because it uses a different scheduler. It uses Slurm instead of PBS, and also it uses a module system. Like a lot of stuff is different there. And while I edited those parts, which can be just like changed with like a different example file or something like that I changed. But there's still a lot of stuff that actually belongs to the old cluster. But and I realized that yesterday that I also missed some parts. So something I knew but didn't put in those materials. But after the workshop, I will go through those notes and really make sure that they are actually showing what's useful on the BP cluster. I will just leave 2 pages there in case you will encounter clusters that, for example, use module systems to load libraries, because that's a very, very common thing that's not present on this cluster, but you will find it on most other clusters. And then I will share this with you to the Telegram group as well, so you can use it as kind of like a reference. It's made in this like really like workshop notes style, but you can use it as a reference. So now I have my notes, and here I need to open PuTTY to start SSH and connect to master UI.
Don't forget to change the appearance.
Yes. So and that was in here.
Mhm.
And the size was 36 or
Around 36.
yeah. Okay. Shift insert is actually another thing I would like to say. So copy paste, Control C, Control V is not something you can use in a Linux terminal, because Control C traditionally means stop executing the current program, like kill the program if possible.
Probably cancel operation.
Cancel operation, maybe, yes. So if you try to use Control C, you will find out not only it doesn't work, but it actually kills your programs. So the older way from all the Unix terminals was to use Control insert and Shift insert for copy and paste. And now this might give you problems on your laptops, because, for example, some of them have the insert key hidden, like for example, need to press this function FN key to get insert. So suddenly you need to press like three keys at once. And I found out that some newer ThinkPads don't have an insert key at all.
Not even with the pi?
Not
MacBook
even
don't have
with
it
that.
at all.
Yes.
Of course, there are differences. There are even like custom keyboards when you have like
Yeah. Then
50 buttons and then
Yeah.
you just add layers, but
no, you then need to.
I thought it's
You then
not.
of course need to find some way to like map insert key somewhere on your keyboard. But yeah, it's like the. I mean, similarly, as I will show you right now. Yeah, I will save the other end for like in a couple of minutes. So we've logged into the cluster. Yeah, if you needed to paste your password, you copy it from somewhere into the PuTTY window, then use Shift Insert to get it there. Yesterday we did some basic stuff with file manipulation in Linux terminal. You remember this ls for like getting the list of files in your current directory, cd to change directories, and cd without parameters. If you get lost, this gets you to your home directory. Those are, I would say, the most important ones. Then there's this empty file that we created, and now maybe we want to put some text into that empty file. For that, you would use some of the editors, terminal editors in Linux. For beginners, I recommend Nano. So if you go Nano, and something I forgot to mention yesterday, auto-completion using the tab key. So if I now, so Linux knows, in some cases, knows what are like the possible continuations of what you are writing on the command line. And if I press the tab key now, it will automatically fill the rest of the text. So that saves you some keystrokes. Enter. This is a simple text editor. Hello world. I'm in a text editor. If you want to save that file, here you have some helpful hints. So this like top arrow sign is used as a visual shortcut for the control key. So control O is to write out or to save the file. So control O, it will ask me for the name of the file. Use this, and then control X to exit. Those who've never used Linux before, if in some tutorial or like someone gives you some advice and tells you to use the probably most prevalent text editor on all Linux system, which is called Vim, called either just VI or Vim. Most of the time they're the same. So you try Vim. Yeah, everyone uses Vim. It's the best editor ever. You'll find yourself in an interface like this, and you'll find out that if you start writing letters, nothing happens. And at some point, you will want to exit this thing. And so, who's never used Linux before? No one? Who's never used Vim before? Everyone knows you've never used Vim. Okay, so now have you opened it on your
I
laptop?
know the joke.
You know the joke, so you know how to exit it.
No, I don't.
Ah, you don't.
I just know that.
So you have the rest of the day to find out. And no. So let me know. Would you have guessed that the exit combination is colon Q exclamation mark?
No way.
You don't have to do exclamation mark.
Yes, you're right. I didn't do any. Okay, I didn't anything. So if you want to edit something in Vim, you first need to press the I key or an insert key that gets you to the insert mode. Then you can actually write letters. Then if you want to exit, you first need to exit from the insert mode using the escape key. And now to go to the command mode, command line, you press the colon. So colon gets you to the command mode, and then W is write, save the file, Q is quit. So this will save the changes. And if you don't want to save your changes, again, escape to escape from the insert mode, then it's Q and like force quit, even if I made changes without saving. So colon Q exclamation mark is usually escape colon Q exclamation mark is the thing to remember. Yeah, so
It's kind of an initiation joke. To tell
Absolutely.
someone open Vim and just figure it out. It's so easy.
I think if you press Ctrl C, it reminds you, it tells you how to exit.
really, that
Uh,
must be some.
Oh, really? It gives you-
Wow.
Maybe
So
it's
there
new,
is the cheat code to it.
Mm-hmm.
but you need to type the column and then.
So let's try if it even works in the this only has Vim. Okay. So like Vim is Vim enhanced.
Yeah.
Yeah. Okay, so just that you know, in case it happens to how to exit it, and if you're not comfortable with it, just use Nano as this easier editor. There's also another way to browse through the files. In program called MC as Midnight Commander. It's a Linux clone of a very old Microsoft DOS program called Norton Commander. And MC looks like this. So you have two panels. You can switch between those panels using the tab key and just kind of what you would expect with, you can browse the files here. So this is okay. You can have different folders open in different tabs. So for example, I open the hello folder in this tab here, and I want to copy, for example, copy this this file to that tab. For that, you have this again those hints down here. So to copy, you should use something 5. And that's my second trend. This is the F5 key. Those F key at the top row of your keyboard, which and in most computers are now shared with those function keys and by default usually used as those function keys. That's the setting I always change the first on any new computer because I really don't use most of the function keys at all. On the other hand, the F keys I use all the time. So you can either use the F keys in case your computer doesn't have the F keys at all. Also can happen. Or in case of some newer Linux machines where some F keys are mapped in by your window manager to some specific other commands, you can use escape and the number. So if I want to copy this file from here to here, I can use either F5 or escape 5, and it will ask me where do you want to copy it? Like by default, it copies to the other open panel. I can just press enter and it gets here. So with the tab, I can switch to that other file, and I can also view or edit it directly from MC. So with F3, I can go to view mode, and I can press F3 again to quit the view mode. And with F4, I get to edit mode, which works similar as Nano. Just here on this cluster in edit mode, it uses this internal MC editor. On some other computers, this can be any different editor, including Vim. To exit from here, I use this F10, and that's the issue with, for example, default GNOME installation, which uses F10 for something, I don't know what. So you either have to redefine Fn in your desktop environment, or use escape 0 to quit. Don't say with exit, just exit. Escape 0 or F10 will also get you out of the whole MC program.
The extra alias is nice. I didn't actually know about escape number. I
Oh.
didn't know about escape number.
Escape number, yeah. That's
really handy.
no, I mean, like I use MC a lot. So the first time there was this new GNOME feature that F10 is mapped to, I don't even know what. So I suddenly couldn't escape MC, and that was like a really, really horrible experience. No, then I realized you can also, of course, escape somewhere, like from file. Well, okay, like now I wouldn't find it because my terminal is too small, but I think it's somewhere in those commands as well. So you can do it from the top menu. You can open and close the top menu, not close, but open using F9. Yeah, but
Yeah, in files there is like below quick CD there are 3 more and then exit.
yeah, okay, that's just exactly the part I don't see. So yeah. So MC can help you with getting your files organized, and for copying the files between your computer and the cluster. You can use on Linux and Macs, you can use the scp command, which works the same way as cp, as like cp for like copying here, like cp hello to hello to. But scp copies between different computers. Now, I don't have, I don't know. Okay, we can try later when I use the integrated scp from the Windows command line.
Installed WinSCP with graphic.
Yeah, I mean WinSCP, of course, like so. WinSCP is a graphical program where I can I just copy the password? And after it logs in, it shows you the contents of your home folder, and actually again a two panel file manager where you can see the files in your folder. But here you can also drag and drop and move files between your computer and the remote computer. And on Linux, you can also use, or on macOS, you can also install MC on your computer, and then you can connect from, well, like one panel of MC can be connected to the cluster, and the other panel connected to the to your local computer. That's also possible, and I can show that. I can show that maybe on the last day from my Linux laptop. But yeah, okay. I mean, like everyone here who's on Linux knows how to copy, how to use SCP. Or like how I have some other. Okay. Yeah, no.
Because it's more convenient that write this SCP commands.
Yeah, but you know some way to copy files between your computer and the cluster. Like
SCP manager.
well, yeah, okay, it's fine. Okay, in that case, let's continue with running running scripts, running job scripts. So yesterday I've showed you this with q sub I sub. Again, you can press the up arrow to recall the last command. Q sub I to get interactive session. So now I'm on A46 node. Exit to exit the interactive session, or Control D. Control D would also make you exit from the login session here, for example. Now, instead of interactive session, we will write a file that contains the commands and put that file in the queue. Then when that file, those commands in those jobs are will be executed, we will get a new file with the output of that command in our home directory, or more specifically in the directory where we submitted the file from. Okay. So let's create a new job file. Give it whatever name you want. The job files are actually shell files, so you can give them the sh extension. It's like a typical one for shell files, but remember, in Linux the file extensions don't really matter, so it also can have no extension. Or my personal favorite way of doing this is to give them the .job extension, so then I always know that, yeah, this is a job file. And for simplicity, you can really just put immediately some command here. With Control O to save the file, Control X to exit. The file does not have the executable bit set. That's a good thing. So already with this, I can put that job in the queue with q sub and the name of the file, and it will use default values for all other possible settings. So with qstat, I can see maybe it already ran because it was like a really short one. So With ls, I will look into my home folder and I see there is this two new files, the same name as the original file, which was also used as the name for the job itself. And one has an extension starting with E, the other with O. So in Linux, text output from your console commands in general go to two different how is it called correctly? Streams, or I don't know now. But like one of them is called standard output, standard out, and the other is standard error. And if you're just working interactively in your terminal, you usually don't see any difference between them because both of them are being shown on your terminal. But by default, running the script in PBS, in the job manager, job scheduler, gives you this error sync in like separately from the output sync. So if we had some errors, oh, there's another way to. I've shown you the less command yesterday to look at the contents of some files. So if I do small job dot, and now if I press tab, there's only one option. No. Now if I press tab, there's two options. So it will first make the, okay, no. So again, I want to get this error file, yeah? So I wrote SM and press tab. That finishes up until here. Now it has three options of what file can it be. And if I don't see those, if I press tab again, so double tap, tells me all the options that are possible continuations of this. So I press .e and tap again. Now it was only one option. You see that file is empty, so that's good. It gave no error. Now I have to exit less with Q. There's another way to display contents of files, and that's especially handy if you know that those files are very short. And that is the command called cat. It's a shortcut from concatenate. It unfortunately doesn't have anything to do with animals. But if I now do cat and the second file, the output file, it has the output of that command hello world, which I didn't tell you that the echo command, what it does is just prints whatever is on the right side of the echo command. So now you see that this is the result that I expected it to be, even if I didn't tell you what exact it will be. Okay, this worked well. Again, what if we want to know if that command was actually not executed on the login node, but on some remote node? Let's edit this script again and add a new line and print the host name of the computer that it's being run on. Again, save with Control O and Control X. Now I submit the same job again. So Q sub small job. Yeah, again, it's very fast, so I will never see it. And you see that I got two new files, E and O with a different number. So this number is the job identifier, the number of the process that has been assigned to the job. So even if you run the same job file over and over again, it will always get a different job number and therefore also different name of those output files unless you would explicitly override that. So let's look into the now my options are one which continues 3 and one which continues 4. So I save that. And hello world was run on node A46. So you should see something similar. Maybe your node number will be different. Yeah. So some more work with the scheduler. I'd like to show you this qstat command finally. So let's just continue with editing our small job example, and I will expand it a little bit. As I said, those files are actually shell files, shell scripts. So in order for the shell script to be like a correct shell script, even if PBS will interpret whatever I put here as a shell script, it's definitely a good practice to start that shell script as a shell script should with this called shebang, which is you put this number sign or cross, or I don't know actually how it's correctly called, exclamation mark, and the path to the program that should interpret this file, so-called shell interpreter. So that usually lives in /bin, and it can be the oldest shell with like less features, or the most common, I would say, recommended shell called bash. So just remember, if you're writing a shell script, always start it with this line. And you can also run the shell script directly from directly as a program from your command line. And let's modify this script so that first we will print the date and time using the command date. Then let's leave everything in here, and then we just wait for 30 seconds, or so sleep 30. What was that? Yeah, Lumlog was off. Actually, it doesn't work. So sleep 30. We'll just wait for 30 seconds, which we can then verify with printing the time, date and time again. With Control O, I save the file. With Control X, I exit. I can again use cat to look at the contents of that file. And now if I send this using qsub, I send it to the queue. And now if I run qstat, I finally get some output out of it, and the output tells me the job ID, which is this process number, and there's this like .torque at it to the ID. Not that important for us now. The name of the job, which now is taken from the name of the file. The user that is running this. Now, as I've learned, the configuration of the cluster is so that QStat only shows you your own jobs. So in user, you will only ever see your own user. On some other clusters, you can also see jobs from other people. Then this will tell you who is running that job. And yes, then if he's there too often and runs his jobs for too long, then you can go to him and tell him to stop. And time is I mean, this sometimes this can get pretty intense, but yeah. Time is the time for that tells you how long has your job been running. Then there's this S. Okay, now in my terminal, this goes to like another line. But if your line is longer, then this is the continuation of the line. So there's this S column, and that tells you the status of the job. Now, R means that the job is running. There are others, and I don't remember how PBS actually calls them. So I'll have to I have to my PBS status codes. Yeah, okay. So because I'm more used to working with Slurm. So the job state is Q, job is queued. That's the very common one. Most of the time you'll see either Q or R, queued or running. Health is that it has been forcibly set not to run for whatever reason. W is if you have scheduled your job to run after a certain time. And move to new location, I've never seen. Yeah, so and exiting, yeah, sometimes, especially for very large jobs, it actually takes some time to stop the job and like return all the nodes to their original state. So on large clusters with large jobs, this can really like take even like an hour, for example, if you're using like 10,000 nodes and using a lot of had a lot of open resources. But most of the time, you will either see that your job is queued and just waiting to be run, or that your job is running. If you see that your job is held, then there is some issue with your, for example, there is some issue with how you specified for example, you requested resources that are and will never be available for you in the queue. I mean, this should be rejected most of the time. But yes, there are situations where you because of the parameters you've set in the job files, it will stay in the queue, but it will never be scheduled to be run. So this basically is wrong. If you encounter this, you should cancel your job and start it again. So canceling a job. Let's say you made a mistake in your job file, or not necessarily in the job file directly, but some mistake in your simulation program settings or whatever. or you see that your job is not being scheduled to be executed at all, so you've submitted the job like this, and now you realized, oh, this is supposed to be run for 5 minutes, and I don't want to have it running for 5 minutes. So you want to cancel this job, and for that, use the command q delete qdel and the number of the job. And now, if I run qstat, the job is not there. It didn't finish early. It really was killed, and that should be reflected in the error file. So this was this last one, this one. So let's take a look. So the first job that finished, the correct one, was this 423 in my case. So it printed the date, said hello world, printed the host name, and then printed the end time. You know, there's those 30 seconds in between those. Now, the other job, the new one, only printed the first date, and then here it was killed. Like from this, I don't know what happened to the job. I just see that it didn't finish what it was supposed to finish. And if I want to see whether there were any errors, I look in the error file, and I don't see anything. Okay. Okay, so yeah, there wasn't any. No, yeah. So sorry, no. But was Slurm? Sorry, Slurm tells you if you forcibly kill the job by canceling it, then Slurm will emit a line in the error file that tells you that the job was canceled by user request. So in this case, it didn't tell us anything. I mean, then yeah, you were on your own to find out what happened, and remember that it was actually you who requested the cancellation of the job. But in any case, qdel and the number of the job. Again, with ls, I can see all my files. If I submit this job, it tells me its number here, but I can also look at the list of my running jobs, and if I want to cancel it, I need to get its ID and the scheduler will kill the job and remove it from the queue. Something I already told you yesterday, but I didn't use it now, and that's that you should try to correctly estimate the running time of your job and put that estimate to the key sub command when submitting the job. Yesterday we did it on the command line. That's not the way you usually do it, and that's also why I was not showing it right now. The way you usually do it is you specify those parameters in the job file. So let's continue, for example, from that same job file and put the PBS parameters here directly in the job script. PBS parameters. Oh, one more thing with the shell script. This number sign is actually used as a comment. So if I comment out, I don't know, this, then this command will not be executed at all. The PBS directives, which control the parameters of the job itself, also start with the comment sign. And the reason for that is that this means that if you try to run this script directly in the command line, it will still work. It will just ignore everything that was supposed to go to PBS. So the PBS commands start with this number sign, comment PBS, and then the parameter, and the same parameter as you would give on the command line, you can put here. So the first useful one is minus capital N, and that gives your job a name. So instead of the name being taken from the name of the file, it can be something you directly put here. Then the next one, the important one, was this duration of the job. So that was minus L whole time equals, and the time. So I don't know what's wrong here with the numpad. It just doesn't work, no matter whether the numlock is on or off. So 0, 0, let's say like 1 minute and 0 seconds. You can also give a special name for the output and the error files with PBS O example output and PBS E example errors. So something like this. Again, Control O to save, Control X to escape. I'll just put it here again with cat so that you can see it if you haven't copied it yet. And you send with Q sub small now with Q stat. You see that the name isn't the name of the file anymore, but the name now says example. And you also, okay, I think I need to kill the job first. But I requested just 1 minute, right? So it's running. I can really wait that 1 minute for it to finish, or I can kill it. And then I should get, yes, I get this example.errors and example.output files. Yeah. And now, of course, what I lost is the ability to have like different the numbered output and error files. So if I don't want to have this in the job, I want to comment out this PBS directive, I can do it with like putting another command sign in front of it. Now it's like comment it out, and not even PBS will read it. There are some more useful parameters for the PBS, and some of them like very important actually. So I would say wall time is like extremely important one. And then the selection of a number of nodes. So if PBS, what's happening? Yeah, I have this, like, if I have a numpad, I have this instinct to use it, and there's some issue with it here in PuTTY. So nodes, and that specifies the number of nodes you want to reserve. So let's say I want to reserve 2 nodes, and also the number of tasks per node. That's a ppn 1 task per node. So this will give me 2 nodes, and on each node I will have one task running. You can also request the minimum amount of memory for your job. So for example, yeah, I mean, like sometimes you don't need that many nodes, but you know, you need some specific amount of memory. So that's mem equals and number in megabytes. So let's say 1.5 gigabyte, that should be definitely free on the, and you can also choose the queue to which your job is assigned, and that's queue, for example, short, because the default one is the long queue. The queues and their meanings, again, you will find in the cluster documentation somewhere. Yeah. So those are the differences between the different queues. Suppose you should be able to get like quickly to the short one if you're not using if you don't actually need the long one, and the others are probably task specific or project specific. So, do you have anything else? Okay, let's try this.
What was this PBS queue short for? There was a line PBS queue short. What was it for?
That's the selection of the queue. So a queue is like the scheduler has several queues in where it puts your where it puts your jobs, and and you can select into which one you want your job to be sent, because yeah, it might provide like different resources. So you see that this long queue is just yeah, like it can only run on certain nodes, while the short queue can run on any node. And yeah, so it's just like depending on what kind of resources you need. And now now I made some mistake. Why cannot processes per node?
G and job per node.
J. Sometimes the question is this PBS Torque or PBS Pro? But then okay, I'll look at it for tomorrow. Let's comment it out. Not using. Yeah.
Out ppm, correct?
Should be. But I mean, there's also this combination of select and CPUs, and where it's like in Slurm when you separate those parameters with the colon. But I mean, I didn't want to do multi-node stuff today anyway. I wanted to show the array jobs, and I'm not even sure if I will have time for that. Well, what time do we want to finish actually?
We already
Finished, right?
Qstat with -a, you can use Qstat -a, and you will see a lot of more information about the job.
Oh,
Qstat -a.
of course, yeah.
Yeah.
If the job is still running.
And you'll see the nodes and all other things.
Yes, good one. Yeah. So again, let's read the second line.
Make it slightly less to be in one line.
Yeah, but I will have to log off and log in again.
For the next
Okay.
time.
Yeah, because like input is somehow like you cannot like change the size of that. But yeah, so that's the session ID. I'm not even exactly sure what's a session ID. Maybe
I think it's okay.
like the runtime. I don't know. NDS is the number of nodes, so you see that I'm running on 2 nodes. TSK, that should be the number of tasks. So since I have a single task per node, I'm only using 2 tasks. And the memory, it's in bytes. Really?
Seems to be so.
Yeah,
it
it's
writes bytes.
bytes,
It
yeah,
writes
yeah.
bytes to me just now.
Okay.
We should add
That's kind of
Maybe
surprising. So yeah, but I thought that. Okay. So PBS comes in 2 versions, the old PBS and PBS Pro, and they have a different way of defining things. So be careful when Googling stuff because sometimes you find stuff for PBS Pro and use it in the or the old PBS and use it in the PBS Pro installation. Obviously, I didn't find the error because the script doesn't basically. I mean, like, yes, the surely 1.5 kilobytes is free on each of the nodes. So, and this is like not like a hard limit in the sense that if your job takes more, it will get killed. It's just like if you request more memory than it's available, it will just not assign you to a node. It should tell you that that what you asked it for is impossible. So let's change it to this should be the this is probably what I wanted to do, right? And yes, now I requested 1.5 gigabytes. So I can delete those jobs, which I mistakenly put there because I wanted to find this nano line again and change it to that many gigabytes, and this should give me some sort of error that it cannot find the resources I requested for the job.
It still launches it, but doesn't give any such maybe
Perhaps because
because
the previous
there is no what
task.
and the status is queued, like it's queued.
Okay, so here it shows that it's
Yes.
queued,
Same.
but it will probably just like never execute because it will never find this. I don't know if it like depends on the scheduler itself or on the configuration of the scheduler. But yeah, if you find your job hung in like such a state, then there's probably some issue with the job itself. Okay, okay, let's, I mean, probably let's finish now. Yeah, because we're already 15 minutes over time, right? And
Delete you.
yeah, I don't know. I
thought-
thought I would actually like find finish earlier with the second part. Maybe we spent too much time on the coffee. I don't know. So the part that will that we will do tomorrow. Tomorrow we will start with this example of parallel programs. So we will do a program, a vectorized program. Then we will do a similar program but using threading, and then we will do a simple program using message passing using MPI, and it will be like combined theory of that stuff and hands-on session of actually doing the programming. But we will at the very beginning we will start with running a so-called array job, because that's like one way of running a parallel program. If you for example have a program where you feed him different parameters and you get different outputs from it, and you want to do a parameter scan, you want to test 100 different parameters, but your program is still a serial program, but you need to run it 100 times. You can make a so-called array job where that program is actually and on the cluster, like to run it 100 times in parallel and get those 100 results faster. So that's what I will show you tomorrow as the first thing. Then we'll move to vectorization, threading, MPI. Okay? So, any questions to that? No? Fine.
We could show a script again, by script.
This PBS script, yeah?
I guess you had the problems with running all the scripts without commenting on the PPN. You should not split PPN and nodes.
Oh,
In one line, so
Yeah. It's
like this
So semicolon,
Yeah.
with
Yeah, exactly.
yes.
with a column. Yeah.
Uh-huh.
Yeah. Yeah. Right. Okay.
But if you send this
Yeah.
job on two nodes, it should work on some processor of this nodes. Yeah, so we should use one processor per node. If you don't specify the number of processors, I think it should use maybe one processor.
Yeah.
each
Okay.
node.
So if I do ppn 2, then you see that I'm running on 2 nodes and using 4 tasks total, because this PPN is processes per node. And by default, it's 1. So yeah, if I just don't put anything,
So
then it's running one process.
Doesn't mean any sense. I mean that PPN1 doesn't mean any sense.
PPN1 is the default.
Yeah. That's the default value. Yeah. Yeah, I mean, everything is set to be killed after 1 minute. So
What can you say about this memory? So, for example, I launched some job. It took, let's say, 10 processors, and this is all processors on our node, on our cluster. So, can somebody launch another job on the same processors on the same time?
not on the same CPUs. If you're asking if I just reserve one CPU, one core on a node which has 16 cores, then this depends on the configuration. In general, yes, someone else can get the other cores as well. I haven't looked into the PBS, but in Slurm, there's this parameter exclusive, which tells you that all the nodes that are reserved should be reserved only for you, even if you're explicitly not filling all the available cores. That's useful, for example, if you are on a server that uses hyperthreading, and hyperthreading is on, and you don't want to use hyperthreading. So you only want to use half of those theoretically available cores. That's a very common use case, because for some simulations, hyperthreading can actually make your program slower because of those shared instruction pipelines.
You mean MPI run oversubscribed, yeah, for hyperthreading? Option for MPI run to use more processors that it's like
No. Just because hyperthreading is a hardware feature of the processor. So if the processor has hyperthreading on, it looks like it has the double the number of cores than it physically has. It's the case here. So you have a CPU that really has only 16 cores, but it looks like it has 32. So if you and again, I don't know the specific configuration here, but the usual thing would be if you then reserve 16 tasks on that node, the scheduler would be free to put another 16 there. But maybe it's not what you want. Maybe you really needed the whole node with only those 16 tasks running. Yeah.
Yeah, but I mean that if you run the job with only 1,500 bytes on the CPU, so can I run another job on the same CPU?
No.
So it reserves
not on the same core.
No. What do you mean by CPU?
The core.
The core. No.
It's taken.
Because here I use a lot of programs on the same cores, and it works.
Yeah, but it's
It's not parallel.
it's not the scheduling. Like you just do everything.
Yeah. No. Okay.
Operational system is the
That's
scheduler.
on a different level. So of course, the operating system itself, it will do some other stuff as well. It's not just running your simulation. It's doing like some whatever its own stuff. So it will use parts of that computational power to do that. What it cannot do is that it would take a different user and
So
make you share that
scheduler
core
can't
with
do
the
it.
different
Scheduler
user.
can't. The scheduler can't do it. if somebody will launch.
No. It's the scale. That's like the main reason basically for it to exist is to make sure that if you wanted one core and someone else, I mean, if you wanted 16 cores and someone else wants 16 cores and you have a 16 core CPU, that you won't be running on the same
Okay,
CPU,
but for
so
example,
that you don't share, so that you really have this full core available to you and you're not sharing it with anyone else.